Now that we know what an acid and a base is, it's time to start measuring the pH of an acid or a base. Now, there's one thing that's going to drive me absolute bonkers, and I hear science teachers misspeak about this all the time. pH is a measure of the concentration of hydrogen or hydronium in a solution. And the two key words there are concentration. Concentration is like molarity, that big molarity, or we'd measure it as moles per liter. And so we're looking for a concentration, an amount of hydrogen in a given volume, and we could also measure that by hydronium. So it could either be hydrogen plus, or it could be that H3O, which really just means that the hydrogen ion is attracted to a water molecule. pH is a measure of hydrogen in the solution. And so we're familiar with the pH scale and that it goes from 1 to 14 and that 7 is neutral, like pure water is neutral at 7. And maybe you kind of remember that it's actually the bases that have the higher pH values. Like the more basic, you'll get pH values that are up in like the 12, 13, 14 range. And it's the acids that are lower. So the more acidic, the lower the pH value, like your 1s, 2s, 3s. These are all your acids, and you might remember that. And I have no problems with that. But here's what drives me crazy. I will go crazy when I hear somebody say this. When they say a strong acid is an acid with a pH of 1, 2, 3. A weak acid is a pH with like 4, 5, 6. And 7's neutral. The strong, weak stuff has nothing to directly do with the pH. Now, there are maybe some coincidences that can sometimes happen, but technically, the strong, weak thing that all has to do with the percent dissociation. pH is about concentration. They're kind of different. I mean, sometimes they might go hand in hand, but not all the time. So it's not accurate to say that strong acid means that it has to have a pH of like 1, 2, 3. Strong just means that it's going to dissociate completely. Dissociation. Whoop, there. And so, I mean, really, you could have a strong acid that dissociates completely. But what if the concentration is really dilute? What if it has a really small molarity? Well, even though it's a strong acid, it might give you a pH of like 5 or 6. pH is a measure of the concentration of hydrogen. And so even though it's a strong acid that completely dissociates, if it has a really small concentration, you're not going to get a lot of hydrogen. And then we'd say that the solution's not very acidic. I mean, it might still be acidic, but it's not very acidic. It's not, I should say it's mildly acidic. I don't like using that word strong. It's mildly acidic. It's got hydrogen. But if the concentration is really small, maybe it's like 0.000 something molarity. Well, yeah, it might dissociate 100%, but I'm not going to get a lot of hydrogen because the concentration is small. And the same thing could be said about a base. Like, I mean, you could have a weak base, but its pH could be like 13 or 14. Maybe it's a weak base, meaning that it doesn't dissociate fully, but it's really concentrated. So it might be like, maybe it's like 15 molar, 15, 16 molar, 18 molar. Well, it's really concentrated. So even though it's weak, meaning that it doesn't dissociate fully, I might still have a lot of hydroxide in the solution just because the concentration is so high. So we have to be careful in that we can't always directly link the strong, weak stuff to pH. I mean, sometimes it might just work itself out that a strong acid has a pH of 1 or 2 or whatever. But then that must also mean that its concentration is substantial enough that we're getting a lot of hydrogen in the solution. And so we try to keep them separate. Strong, weak depends on the tendency of the particle to dissociate. The pH measures the amount of hydrogen in the solution. It's going to look like this. To calculate pH, we'll use an equation. pH equals opposite log of the hydrogen or hydronium ion. So, I mean, often you might see it written either way. You could see like the H plus or H3O plus. They're the same thing. Opposite log of the hydrogen or hydronium. And whenever we see something in brackets, that brackets means concentration. Concentration, which for solutions we're going to measure as big molarity. Or maybe they'll just write moles per liter. Okay, so math lesson, which I don't know the last time that you did logs in math, but here's our like nickel tour of the LOG log base 10. So the LOG log base 10, we're not talking like natural logs or e to the whatever. The log base 10 is going to be the exponent of 10. So if I have a concentration that's in scientific notation, like this 1.0 times 10 to the negative 12, the log is just the exponent of 10. So the log is 12, or I should say negative 12. But pH is opposite log. So pH then is really the opposite exponent of 10. So maybe we'll just make like a little note. In case you have to brush up on your logs, pH is going to be the opposite exponent of 10. The opposite exponent of 10. We're going to try to put our concentrations in scientific notation when possible. That'll just make it a little bit easier. So if I saw this 1 times 10 to the negative 12, and you can plug it in your calculator if you want to. You could just plug in the opposite LOG log key and then hit 1.0 times 10 to the negative 12. But really, it's the opposite exponent of 10. It's 12, which tells me that it's a base. Now, most likely, it's a pretty strong base, that it's probably something that's going to produce a lot of hydroxide. Like a pH of 12 is pretty basic. In the second one, if I go opposite log, 1.0 times 10 to the negative third, pH is just the opposite exponent of 10. The log base 10 is just the exponent of 10, and pH is the opposite exponent. So this is going to be 3. So probably pretty acidic. Maybe it's a strong acid, something that's dissociating completely. Or if it's a weak acid, it would have had to be pretty concentrated. My guess is this is a strong acid because that molarity is pretty small. And I'm still getting a pH of 3. Now, another like math review. We have to kind of remember what these exponents mean. These negative exponents of 10. So that if I have a number that's like 1.0 times 10 to the negative 12, and I want to take that out of scientific notation, I got to move my decimal spot backwards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There it is. That's going to be crazy small. crazy small. Well, we're really talking about a concentration of hydrogen. Well, if it's a base, it's not supposed to have a lot of hydrogen. Bases have a lot of hydroxide, not hydrogen. So the amount of hydrogen in this solution is super, super tiny that it is not very acidic. And in fact, with a pH of 12, we would call it a base. If I have a concentration of like 1.0 times 10 to the negative third, and I take that out of scientific notation, I'm going backwards just 1, 2, 3. So it's really like 0.001 molar. And then that is the concentration of hydrogen. So now if I compare the two, I mean, this is still a small number, but it's bigger than this number. And when we're talking about an amount of hydrogen in the solution, this would be more acidic. And this being so small, we'd really end up calling it a base. But there's a very insignificant amount of hydrogen. And who could even measure that realistically? I can't measure that number in our lab, 10 to the negative 12. That's crazy tiny. Now, here's one more example. Let's say I have 1.0 times 10 to the negative third versus 1.0 times 10 to the negative fourth. And now I want to take this out of scientific notation. And I want to go like 1, 2, 3, 4. So this would really be like 0.0001 molar hydrogen. So we just have to kind of remember that these exponents being negative, this 10 to the negative fourth, this is a smaller number than 10 to the negative third. This is a larger number. And when I take them out of scientific notation, I kind of notice that really this is more hydrogen. This is less hydrogen. So when they ask me which is more acidic, people always want to say like, hey, it's this guy. Or like, really, this is pH 3. This is going to be pH 4. And they want to say that the pH 4 is more acidic. The number is higher. But we kind of have to remember where that pH number is coming from. It's coming from a negative exponent of 10. That really, when you say then that the concentration is 10 to the negative fourth, that's smaller than 10 to the negative third. This pH 3 represents a solution that has more hydrogen. And in fact, this solution has 10 times more hydrogen than the pH 4. Because we have to think that these pH numbers are exponents of 10. So when I say that this has 10 times more hydrogen, it means that it's like a power of 10 greater than this guy. And so sometimes I think that's where people get a little goofed up by saying that like the higher the pH number, the more acidic. But really, when you put that pH number in perspective, it's a negative exponent of 10. The higher the pH value, it turns into a smaller concentration. 10 to the negative 12 is a crazy small amount of hydrogen. That in fact, the solution is really a base. And now when I compare these two, yeah, a pH of 4 ends up being 10 times less hydrogen. It's a power of 10 less compared to this 10 to the negative third. So anyways, there is my 10-cent tour of exponents and log base 10. If that is not something that you've done in your math class, then maybe let me know. I mean, we're not going anything crazy beyond this. And a lot of it can be done in a calculator, but just conceptually, if you haven't worked with logs, then maybe stop by sometime and we can just look at this a little bit more closely. Okay, so then here's kind of where I want to wrap things up. That water really exists as what we call an equilibrium system. I mean, there's a whole bunch of water molecules in a beaker, and notice again that double-sided arrow. We were looking at that back in some of those weak acid, weak base equations. That these water molecules being liquid tend to move around, and when particles have a little bit more movement, they tend to collide more often. And sometimes water molecules will just collide with themselves and transfer a hydrogen. What? So just as these guys collide, it's possible that one hydrogen is transferred between the two water molecules. We call this the self-ionization of water. Water like self-ionizes, where usually water molecules are neutral, but every now and then it's possible that they collide with each other in the perfect orientation such that a hydrogen is transferred. And then we produce our friends hydronium and hydroxide. It looks like these pictures where the H3O ends up being this guy, hydronium, and the OH is this guy, hydroxide. Self-ionization of water. Sometimes, not very often, but sometimes the water molecules move and collide in a way that they self-ionize. They form ions just from each other. There's a transfer of an electron forming charged particles. Every now and then people will kind of say, like, this pH scale is weird. Who made up this pH scale that goes from like 1 to 14 and 7 is neutral? Like, who made that up? And, like, why doesn't it go from 1 to 10 and 5 is neutral? What's 7? Well, it's this. It has experimentally been determined that in a pure sample of water, the real concentration of hydrogen or hydronium and hydroxide is 1.0 times 10 to the negative 7th. And we could say like big M for molarity or moles per liter. That has been experimentally determined that in a sample of water, there would be 1 times 10 to the negative 7th moles per liter. If I had a liter of water, there's 1 times 10 to the negative 7th moles of H3O, or hydrogen, and hydroxide. So it's really small, which makes me think then that in a liter of water, 99.999% of all the particles are really neutral water molecules. It's just on a very rare occasion that we get this self-ionization. Oh, well, here's why the pH of water is 7. When we look at that pH equation, pH is opposite log of the hydrogen concentration or hydronium, H3O plus. They're the same numerical value. Well, you plug that in, you plug in this number. It's experimentally determined that this is the amount of hydrogen, and it's also the amount of hydroxide, because they are formed at a 1-to-1 ratio. But technically, pH, the H in pH, stands for hydrogen. If you plug that in, you're going pH equals opposite log of 1.0 times 10 to the negative 7. pH is the opposite exponent of 10. The pH of pure water is 7. And it's not that somebody made up this scale. It's just that it has been experimentally determined that that is the amount of hydrogen in a pure sample of water. So this is one of the equations that we'll use quite a bit when we look at solutions and measure how acidic or how basic they are. The other one that we'll use is this. For any solution, it could be an acid, it could be a base, it could be water. For any solution, if you take the hydrogen concentration, which again, that could also be H3O plus hydronium, and you multiply by hydroxide, the product will always be 10 to the negative 14th. That's a constant. These are the two equations we'll use in this acid-base unit. For any solution, hydrogen times hydroxide is 10 to the negative 14. Now, in the case of neutral water, this 10 to the negative 7th, that is the concentration of hydrogen and hydroxide. They're the same. It's a 1-to-1 ratio. And so if you really multiply 10 to the negative 7th times 10 to the negative 7th, you get 10 to the negative 14th. Wow. So in a neutral solution, the hydrogen concentration equals the hydroxide concentration. Neutral just means that there's the same amount of hydrogen and hydroxide. In a pure sample of water, it's neutral. They're formed at a 1-to-1 ratio. If something is acidic, the tables will turn so that the concentration of hydrogen is greater than the concentration of hydroxide. Now, it might still be that there is some hydroxide there, but the hydrogen concentration will be much more significant. If the solution is a base, it flips again, so that now the hydrogen concentration will be less than the hydroxide. Oh, cool. Again, there might be some hydrogen present, but when I look at the concentrations, there will be significantly more hydroxide in a base. But no matter what, for any solution, if you multiply these two concentrations together, you will always get a constant 10 to the negative 14th. And we'll look at how that can be used later on in this unit.